Here we are with chapter 17, and we're dealing with refraction as the main concept in this chapter and looking at Snell's law. So we started off looking at smooth surfaces, and smooth surfaces produce regular reflections. What is meant by that is if you're following the beams of a laser light, so this is a mirror, and here comes in these parallel beams of light that are coming from this laser. We're looking at a kind of a microscopic scale of this. Okay, these are going to bounce off with the same angle that they come in. So if you remember, these are going to reflect off at the same angle like that. So the angle that's coming in, this is going to be called your angle of incidence, or your theta I. Okay, so your theta I, let's take, well, it's kind of hard with this because we've got three rays going here. Here's your angle of incidence, and then we have your angle of reflection. So angle of reflection is going to be theta lowercase r. And then when you have a regular reflection like this, you're going to have your angle of incidence being equal to your angle of reflection. Remember, it's measured to the normal. It's not measured from down below here. So if this is 20 degrees, your angle of reflection will be 20 degrees. Nothing to do with 70 degrees down here. Rough surfaces produce diffuse reflections. Okay, I had aluminum foil with these parallel rays of light coming in. Parallel rays of light. And it might have looked something like that. It scattered the light because this was not flat. So each photon of light, in theory, would be having a regular reflection, but when you have your beam of light coming down, it scatters all those parallel rays of light. Reflection and refraction of light off of a surface. So we talked about reflection right here. Refraction is when we bend the light in a different material. So refraction is when we bend the light in a different material. So the angle of refraction we're going to call theta r. And let's use this space right here for our glass square slide, if you remember that. I had a laser beam, and it was coming in at a certain angle. And here's the normal, which again is 90 degrees to the surface. We had some of our rays that were coming off with a regular reflection, but then what we also had is we had the refraction of that beam. It did not continue on a straight path, but it bent inward toward the normal. So this is going to be your angle of refraction. So here's your angle of incidence, there's your angle of reflection, there's your angle of refraction. Okay, and the optical density of this material is more dense. So this right here is a denser material. The air is less dense. And if you remember, when it comes out of that, here's the normal again, and it bends away from the normal. So here would be theta R1, or R prime, or R2. Yeah, let's call it R1 and R2. This angle, the refracted angle going out, is equal to the incoming incident angle because it's being refracted inward and then outward within the same material. So whether the light is refracted toward or away from the normal when it passes from denser to a less dense material. Light is refracted toward or away from normal when passes denser or less dense. When it's going into a denser material, like it's going from air to air to glass, for example, air to glass, okay, the refraction is toward, it bends toward the normal. Here it bends away from the normal. So when you're going into a less dense, when you're going from glass to air, it's going to bend away. Know how the angle of refraction will differ from angle of incidence when passing through a medium. So if you're going into a denser material, which is larger, your angle of incidence or your angle of refraction? Your angle of incidence will be larger than your angle of refraction. When you're going into a less dense material, your, like from here to here, your angle, your second angle of refraction will be greater than the original right here. Because it's bending away from the normal, the angle will be larger. So your outgoing angle will be greater than the refraction coming into the material. Angles of incidence larger than the critical angle will create total internal reflection. So this critical angle, this is going to be a mathematical concept, this is the critical angle that produces a 90-degree refraction. Produces 90-degree refraction. Okay, let me try to draw this. Imagine that you have a surface like this, and you're coming below from water. If you remember, we went from water to air. Okay, and let's say this is the normal here. So this angle coming in like this is going to be going into a, here's the angle of incidence. We're going to be refracting this angle. We're going from water to air. So this is not going to continue on a straight path. It's going into a less dense material. It's not going to bend toward the normal. It's going to bend away from the normal. Let's draw a solid line right here. There's this critical angle, which is measured from the normal to this angle, that produces a perfect 90-degree refraction, and it still works with Snell's law. So as the angle is less than the critical angle, you're going to get refraction. When it's equal to the critical angle, you're going to get a refracted angle of 90 degrees right here. However, if you're larger than the refracted angle, you're no longer going to have any refraction. You're going to have total internal reflection. That's the total internal reflection. That's this dotted line right there. How refraction produces rainbows and how millions of droplets are needed to produce rainbows. So what we have is, let's say this is TIF. Okay, this is going to be total internal reflection. What we have is we have total internal reflection inside each raindrop. each raindrop acts as a prism. So it separates those light. Then we get total internal reflection. Then those will then leave the raindrop and then come to our eye. So each drop is a prism. And each drop sends one color to your eye. So we need millions of drops, possibly even trillions of drops. Need millions of drops. Well, if that one drop produced one color, and you have two drops that produces a second color, we have to have all those colors that are in between. Even if you have red and orange, you have to have red, orange, then you have to have red, red, orange, then you have to have red, 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 orange, etc., etc. So you need millions of drops to create the continuous spectrum. Here are the calculations. Calculate the indices of refraction or angles using Snell's law. Okay, so let's see. Let's go to this right here. Use the index of refraction to find out the speed of light. Here's the formula for the speed of light. And of course, your velocity is always going to be less than the speed of light, because in a vacuum, this is going to be 1.0. Okay, so if you're going to increase your index of refraction, because you can't go any faster than the speed of light, what's going to happen is we're going to decrease the velocity. So we can't have anything faster than the speed of light. So what's going to happen is our velocities of the substances are going to decrease inside our materials, such as glass or quartz or diamond, and that's going to increase the index of refraction. Use Snell's law to calculate the critical angle that produces a 90-degree. This is a problem that a lot of students miss. So when looking at Snell's law, here's Snell's law here. Okay, the index of refraction for the incoming or angle of incidence times the sine of the angle of incidence equals the index of refraction for the refracted material times the sine of the refracted angle. Let's look at the definition for critical angle. Angles of incidence larger than the critical angle will create total internal reflection. Well, the critical angle is that which produces a 90-degree refraction. That's going to be 90 degrees right there, not this one right here. This is the critical angle that we're trying to calculate. So calculate the critical angle. The critical angle is going to be this right there. Okay, and you're coming from water, as we were doing in the lab, and going into air, which is 1.00 up there. Okay, that's about it for chapter 17.